For a long time, the Milky Way was seen as a barrier, a glowing wall of billions of stars, dust, and gas that blocked our view of what lay beyond. No matter how powerful our telescopes were, that thick band in the sky, known as the zone of avoidance, acted like a cosmic curtain. A curtain that may have been hiding a crucial part of the observable universe. Behind that curtain, quite literally, millions, or rather billions, of objects were there all along. Entire galaxies, stellar systems, cosmic clusters, all camouflaged by the very galaxy we call home. And now, for the first time, we've managed to peek behind it. What scientists discovered wasn't just surprising, it was revolutionary. Imagine spending decades staring at a wall, never knowing that behind it was an entire city, pulsing with lights, skyscrapers, and life. That's exactly what happened. The difference? This city contains billions of cosmic structures, and they're millions, even billions of light years away. Thanks to highly sensitive radio telescopes and advanced AI-driven mapping techniques, we've pierced through this cosmic shadow zone. Where once there was only noise, there's now a detailed map filled with previously unknown objects, 1.5 billion of them. And we're not talking about debris, dust, or background noise. These are entire galaxies, many larger than the Milky Way itself, some collapsing, others being born. Among them are exotic stars, active black holes, and radio sources showing patterns we've never seen before. This discovery rewrites everything we thought we knew about the structure of the universe. For decades, cosmic maps displayed a strange void behind the Milky Way. Not because the void was real, but because we simply couldn't look through. Now that void is overflowing with more information than any other region of the sky. Even more intriguing, the way these objects are distributed suggests there are cosmic forces at play on scales we don't yet understand. The Milky Way's own gravity may be bending and concealing far more than we ever imagined. Why does this matter? Because understanding what lies behind the Milky Way also means understanding our true place in the universe. And that could take us into a new era of astronomy. Maybe the most important since the discovery of the cosmic microwave background. The Milky Way has always been a border, a bright, dense veil stretching across the night sky from end to end, hiding what lies beyond. For centuries, astronomers have wondered what could be lurking behind this stellar curtain. And for a long time, that question had no answer. Our very own galaxy blinded us, like trying to map a forest from the inside, surrounded by fog. But everything started to change with the rise of a new generation of instruments, capable of seeing what human eyes never could. Using radio waves, deep infrared, and advanced noise-canceling algorithms, modern telescopes began piercing the Milky Way's background like opening windows in a wall. And what they saw on the other side wasn't just surprising, it was dizzying. Instead of a void or a few scattered galaxies in the distance, the data revealed a vast sea of invisible points, galaxies, stars, clusters, and countless unidentified objects, more than 1.5 billion of them. Literally, a cosmic wall compressed behind the Milky Way. This wasn't just a technical breakthrough. It was a rewrite of our understanding of the observable universe. These objects aren't all at the same distance. Some belong to what astronomers call cosmic superstructures, walls of galaxies linked by dark matter filaments, forming a cosmic web that stretches across billions of light years. Others seem to clump together into densely packed zones, as if certain parts of the universe grew faster or heavier than others. And we still don't know why. Among these structures, one name stands out: the zone of avoidance, or ZOE. This zone was a blind spot in cosmic maps, a portion of the sky blocked by the dust and star clouds of the Milky Way. But now, thanks to these new observations, the ZOE is emerging as one of the most densely packed regions of galaxies in our local universe. But it doesn't stop there. Within the ZOE, scientists detected regions that appear to be gravitationally interacting with our galaxy, subtly influencing its shape and motion. In other words, there's not just a universe behind the Milky Way. There are hidden forces shaping our own position within it. This insight has opened new paths of research into gravitational waves, dark matter, and the motion of the local group. the cluster of galaxies that includes our own. And most intriguing of all, many of these 1.5 billion objects remain unclassified. Some of the radio and infrared sources don't match any known galaxy, star, or black hole. That means we might be facing entirely new categories of cosmic bodies, or at the very least, exotic forms of matter and energy we've never encountered before. Even more bizarre, scientists have found unusual geometric patterns in the way certain clusters are distributed. In some regions, objects seem to form parallel lines or smooth arcs, as if following a hidden logic, perhaps shaped by ancient cosmic collisions, or just maybe traces of intelligent design on a galactic scale. Of course, that's speculation, but even that can now be studied with new seriousness, given the unprecedented volume of data. With each new layer revealed, our picture of the universe changes, and maybe, for the first time, we're beginning to truly see what's really out there without the filter of our own galaxy. As we peer into the vastness behind the Milky Way, we're reminded that discovery is not just about pointing telescopes and counting light points. It's about inventing new ways to see the invisible. This phase of exploration didn't triumph with metal and glass alone, but with lines of code and sophisticated algorithms. First came the ultra-sensitive infrared probes, equipped with detectors capable of picking up heat signatures even in the coldest, dustiest regions. These instruments map not only luminous stars, but also objects without their own glow, brown dwarfs and rogue planets drifting alone through deep space. By penetrating the dust, they outline soft silhouettes that once eluded optical telescopes. Next, the new generation of radio antennas carved a path. Gigantic arrays spread across deserts and plains synchronize observations in real time, like an orchestra of dishes playing a galactic symphony. Each radio pulse, each sky sweep, records not only bright sources but distant pulsars, cold gas clouds, and even echoes of supernova explosions long faded. These signals arrive intertwined, static in harmony, and demand powerful digital filters to isolate the meaningful data. But the masterstroke came with artificial intelligence. Neural networks trained on enormous catalogs began recognizing patterns invisible to the human eye. They learned to spot life peaks in X-ray data, subtle signatures hinting at black holes devouring matter, and to distinguish a compact galaxy cluster from a casual grouping. With every new dataset, these models refine themselves, guiding astronomers to the most scientifically valuable targets. And that's not all. Merging different wavelengths, visible light, infrared, radio, X-rays, even gamma rays, is done in multimodal experiments where each band complements the others. An object silent in visible light may blaze in the infrared, while a faint radio source might turn out to be an intense gamma ray emitter. These overlays produce composite images, akin to cosmic X-rays, revealing layers of information once hidden. To process billions of objects, we also developed automatic star scanners. These systems continuously sweep the sky, with algorithms detecting anomalies in fractions of a second. A previously uncharted region can trigger an alert, redirecting telescopes instantly to capture the scene across multiple colors and wavelengths. It's like having a cosmic watchtower always on guard, ready to catch any fleeting event. The data then streams to processing centers around the globe. Supercomputers crunch petabytes of information, equivalent to entire libraries, in search of correlations, repetitions, and statistical patterns. Each new correlation refines our cosmological models and helps set priorities for future space missions. Finally, we are testing autonomous probes designed to venture into the shadowed regions. With ionic thrusters and foldable solar sails, these compact vessels could position themselves on the other side of the Milky Way, observing the hidden sky directly. Unobstructed by our galaxy's glare, they would return unparalleled images and measurements. Thanks to these tools, the map of 1.5 billion objects gains sharper contours, and our imagination is challenged to understand not just what lies behind the curtain, but how it interacts with the entire cosmos. Each technological leap extends our senses, enabling discoveries that, until yesterday, seemed pure science fiction. Now that we have unveiled the vast tapestry hidden behind our galaxy, the question arises, what does it all mean for modern cosmology? The answer lies in one of contemporary physics' greatest enigmas, dark matter, and in the fundamental principles governing the universe's structure. By mapping 1.5 billion objects, we observed gravitational lensing patterns that don't perfectly match standard model predictions. In certain regions, background light is bent far more dramatically, suggesting reservoirs of unseen mass beyond what baryonic matter can explain. This points to localized concentrations of dark matter, perhaps dense bubbles that influence not only local gravity, but also how galaxies grow and collide. These discrepancies lead to another question. Must our assumptions of cosmic isotropy and homogeneity be revised? The existence of pronounced superstructures and voids, now confirmed behind the Milky Way, reinforces the idea that the cosmic web is more complex than we once thought. If these concentrations of galaxies and dark matter span billions of light years, in a non-uniform fashion, we may need to rethink how we define the homogeneity scale, the threshold at which the universe transitions from irregularity to uniformity. Moreover, the gravitational anomalies we detected could shed light on the much-debated Hubble constant tension. The universe's expansion rate is measured differently via local supernovae versus the cosmic microwave background, and the results don't align. If unaccounted mass concentrations exist near us, they could be skewing part of those measurements. Better understanding the dark matter distribution behind the Milky Way might help reconcile these values. Our view of baryon acoustic oscillations also gains new life. These sound waves in the primordial universe left subtle imprints on galaxy distribution. The expanded mapping, now including previously inaccessible regions, offers a natural laboratory to test how these oscillations manifest in newly revealed structures, comparing against theoretical predictions derived from the cosmic microwave background. But there's more. This discovery paves the way for multi-messenger astronomy. If these hidden clusters harbor massive black holes, galaxy mergers, and titanic explosions, we should expect an uptick in detectable gravitational wave events like black hole or neutron star mergers from directions we once overlooked. Coordinating radio, optical, X-ray, and gravitational wave observatories will be crucial to capture these phenomena in real time. From the standpoint of galaxy formation, accessing these concealed territories is like finding the missing pages of a manual. We can compare properties of young and old galaxies in both high and low density environments to better understand processes like supernova feedback, black hole jet ejections, and the role of the intergalactic medium in star formation. And we can't forget upcoming missions. Telescopes such as Euclid, Roman, and the James Webb are poised to extend this cartography, delving deeper into the infrared and microwave bands. Plans for radio observatories on the moon's far side aim to eliminate terrestrial and galactic interference entirely. Every new mission will be guided by this map, pointing to the most promising locations, both for groundbreaking science and potential clues to exotic phenomena like self-interacting dark matter or, dare we say, remnants of ancient civilizations. If that doesn't sound entirely outlandish in a universe this vast. Finally, we must consider the philosophical dimension. By revealing a more intricate and secret-laden universe, we reaffirm the Copernican principle. We occupy no preferred place, but are part of something immeasurably larger and more mysterious. Each new galaxy discovered behind the Milky Way reminds us that human knowledge is always provisional, and that the next scientific revolution may lie exactly where we once feared to look. Millions of years ago, a cosmic event may have unfolded beyond the Milky Way, creating a region of space where time and space behave in radically different ways. In that hidden zone, home to the 1.5 billion newly discovered objects, parallel dimensions or baby universes could be evolving independently of our own. These objects might be remnants of alternate realities, governed by their own physical laws and perhaps even harboring life, yet still visible to our most advanced telescopes. Such parallel realms may have emerged in the aftermath of the Big Bang or as a result of fractures in the fabric of space-time. What we perceive as a wall of cosmic objects may in fact be the boundary between interwoven dimensions, and their seemingly random motions could reflect gravitational interplay among multiple universes and exotic cosmic forces. Rather than distant galaxies or stars alone, Some of these points of light might be entities caught in perpetual transition between different states of existence. According to the baby universe hypothesis, this hidden region may contain nascent universes, stellar nurseries, embryonic galaxies, and protoclusters still under construction, poised to evolve into celestial structures akin to our own. The particles and radiation we detect could be echoes of these realities, their signals, distorted by the vast reaches of space-time before arriving at our instruments. Adding to the intrigue, supermassive black holes lurking beyond our galaxy might act as interdimensional gateways, not merely devouring matter, but transporting it between universes and weaving an invisible network of cosmic connections. If this theory holds true, the implications for exploration are staggering. We might one day encounter entirely new forms of life, multidimensional beings shaped by laws foreign to our own, possessing senses and abilities beyond human imagination. Future technologies could enable interdimensional travel, navigating these cosmic portals and opening pathways to realms of unimaginable diversity. Ultimately, recognizing that our familiar notions of time and space apply only to our own universe could spark a paradigm shift, revealing that the cosmos is far more expansive, complex, and mysterious than we ever dared to dream. If this journey through parallel dimensions and baby universes got your heart racing, smash that like button and subscribe so you won't miss any mind-blowing discoveries. Drop a comment. Which interdimensional portal would you explore first? Let's uncover the universe's secrets together.